Okay, we're back. 3.3, Factor Theorem. Consider the special case. Well, let's pick green today. Consider the special case when the remainder equals 0 or r equals 0. Okay, we have this thing called the factor theorem. It states that if p of a equals 0, then x minus a is a factor of p of x. If x minus a is a factor of p of x, then the reverse is true. P of a equals 0. Let's investigate. X cubed minus 7x minus 6, determine whether all of these, right, is x plus 1 a factor. So p of negative 1, let's evaluate. That equals equals 0. This is a big yes. This is a factor. Next one. P, remember, x minus a, so a is equal to 1. So p of 1 equals 1 cubed, so you get the idea. So let me run through these examples. That's 1 minus 7 minus 6. Okay, it equals negative 12, right? We need it to be equal to 0 in order for x minus 1 to be a factor. So since it equals negative 12, this is no, not a factor. Remember, x minus a is equal to negative 2 this time. This is equal to 0. So p of a equals 0, then yes, this is a factor. No, not a factor. Okay, I'll pause it right here. Go through the rest of the examples yourself. Okay, and then check your answer. I think you get the idea of what we're doing here. So I'm just going to finish these up. Okay, let's complete the statement. The maximum number of linear factors of p of x is equal to the degree of p of x. Since the factors of p of x are, so what were our factors? Right here. So all the yeses. Right there. And right there. 3 factors. Let's finish that statement. Since the factors of p of x are x plus 1, x plus 2, and x minus 3, then we can rewrite p of x in factored form as p of x equals x plus 1 times x plus 2 times x minus 3. Okay, number 2, determine the zeros of the function using your graphing calculator. How are the zeros of a polynomial function related to the factors of the polynomial? Here's my window. Okay, and this is what I get. There's one factor, x plus 2. There's another factor, x plus 1. And then there's my third factor, x minus 3. Okay, observation. So f of x equals x plus 2 times x plus 1 times x minus 3. Let's answer this question. How are the zeros of a polynomial function related to the factors? Well, zeros are the solutions to the factors of the polynomial. So x plus 2 equals 0. X equals negative 2. That's the 0. This is the factor. So right there. Let's make a general statement here. When dividing by a divisor in the form x minus a, and the result is a remainder of 0, then the divisor is also a factor of the polynomial, which the polynomial is also called the dividend. Which brings us to the integral zero theorem. If x equals a is an integral 0, so integral not integrating for calculus. This means they are integers. As numbers, they are integers. Remember integers? Negative integers are -3, -2, -1. 0 is also an integer. 1, 2, 3, and so on, right? So those are integers. So if x equals a is an integral 0 of the polynomial p of x with integral coefficients, then a is a factor of the constant term of p of x. The integral 0 theorem indicates which factors to test when attempting to factor a polynomial. Okay, state the corresponding binomial factor of a polynomial p of x given the value of the 0. Okay, remember this is in the form p of a equals 0, so a equals 5. If we're in the form x minus a as one of your factors, okay, then x minus 5 is your factor. P of a equals 0, a equals -8, and we're in the form x minus a, x minus -8, then x plus 8 is your binomial factor. Okay, example 2. State the possible integral zeros of the polynomial p of n equals n cubed plus 4n squared minus 15n minus 18. Okay, this part. This is important when we're learning how to factor these giant polynomials. a is a factor of the constant term of p of x. Here's the constant term, negative 18. So a, the possible factors of this polynomial, have to do with the a value, which is a factor of the constant term. So what are the factors of negative 18? Okay, so quick aside here, remember 1 times negative 18 equals negative 18, and negative 1 times 18 also equals negative 18. So you'll see there's a whole bunch of plus minus values. You can do this for all the other pairs of factors. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18. So those are all the possible factors of negative 18, and those are possible factors of the polynomial itself. Example 3, if p of 4 equals p of negative 2 equals p of 1 equals 0, state a third degree polynomial p of x in factored form. Is there only one answer? Well, let's see. So we're saying p of a equals p of b equals p of c. A equals 4, b equals negative 2, c equals 1. Okay, so what are our factors? X minus a, x minus 4, x minus b, x plus 2, x minus c, x minus 1. So one way to state p of x is multiplying the three factors together. Is there only one answer? No, there's more than one answer. More than one answer. We can throw a coefficient in the front like this. Let's put 7. If you graph this on your graphing calculator, so graph this, you'll see that all the zeros occur at the same spot, except the shape of the graph is going to be different. Okay, but it will still retain the same zeros and the same factors. Okay, steps to algebraically factor a polynomial fully. Determine all possible factors of the constant term using the integral zero theorem. Find a factor by evaluating p of x or value of x by using the factors from step 1. Use synthetic division. Factor further. State your answer. Okay, those are the mathematical instructions. Let's go through a couple of examples to illustrate this. Actually, lots of examples. Okay? All right. Example 4. Algebraically determine the factors of the polynomial function p of x equals x cubed minus 6x squared plus 3x plus 10. Step 1. Factors of, what's my constant term? Integral zero theorem. There's 10, right? Factors of 10. Remember, as an aside, an example is, remember, negative 1 times negative 10 equals 10. Also, 1 times 10 equals 10. Okay, so we have positive and negative values that matter. So factors are plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. So we've identified all the possible factors of the constant term. Now, this next part is just trial and error. We're going to use the remainder theorem. Okay, when we do the remainder theorem, remember, we're looking for p of a equals 0. If we plug in any of these, so these are called possible a values. So we're looking for factors, right? When we plug in the possible a values, will we get 0? If we get 0, then we know it's a factor. If we don't get 0, it's not a factor. So a lot of this will be trial and error. Okay, let's give it a shot here. I'm going to start with 1. P of 1. That equals 8. So not a factor. Remember, we're looking for 0, right? Let's try p of -1. Another possible a value. Yes. So a equals -1 is a factor, or I should say x plus 1 is a factor. Okay, so let's take that step 3, synthetic division part. Now that we have an identified factor as x plus 1, remember a equals -1, x minus a is the form, so x minus -1, x plus 1. So when we synthetically divide, the divisor is -1. Let's make a long row here, 1. So we're dividing this polynomial. That's the dividend. So 1, -6, 3, and 10. Okay, 1 plus 0 is 1. Okay, let's step through this. And as we expect, remainder equals 0. So that verifies that that is a factor. Number 4. Factor further if possible. So from here, let me just write this in red to highlight this. Remember the quotient, so the bottom part here, quotient, that's x squared minus 7x plus 10. Step 4 says factor further if necessary, and it is necessary. Remember, we're trying to determine all the factors. Okay, so we need to factor x squared minus 7x plus 10. Oops. So when we factor that, that's x minus 5, x minus 2. Step 5, final step. State your answer in fully factored form. P of x equals x plus 1 times x minus 5 times x minus 2. So let me highlight this to show you where all the factors come from, all the links. Let's see, we have x minus 2, that was from the factored form. We have x minus 5, also from the factored form, step 4. And then the last part is we have x plus 1. Where did that come from? That's right there, right? Remember this x plus 1? This is the factor that we got right here, right? That's through a little bit of trial and error. Okay, next page. Okay, example 5. Algebraically determine the fully factored form of x to the 4th minus 3x squared minus 7x squared plus 15x plus 18. Verify it graphically. So we're going to do this through the trial and error method again. And we're going to verify this graphically. Okay. So the integral zero theorem states that, look at the polynomial, look at the constant term. What are the possible factors? Okay, this will take some trial and error. You have to be patient. Okay, it is a bit of a guessing game. These are all, remember what this is? These are possible a values for our factor x minus a. Okay, let's try a equals 2. So try a equals 2. So we're looking for P of A equals 0. If that's the case, then A equals 2 is one of our factors. So let's try P of 2 equals 2 to the 4th minus 3 times 2 cubed minus 7 times 2 squared plus 15 times 2 plus 18. And we got 12. So this does not equal 0. So not a factor. Okay, so A equals 2 doesn't work. Let's try A equals negative 2. So we're looking for the condition, does P of A equals 0? So P of negative 2. And let's work through this example here. So yes, this is a factor. Yay. All right. So what do we do with this at A minus 2? We can do the synthetic division. So A equals negative 2. So x minus A is x minus negative 2. So the negative 2 goes on the outside. And let's synthetically divide. Okay, let's do this. Okay, this 0 tells you that the remainder is 0, so that checks. Okay, so we know that x plus 2, that's a factor, but what's left over? We need to fully factor this, right? So that is x cubed minus 5x squared plus 3x plus 9. We need to factor that more. So let's apply all these steps again. Look at the constant term 9. What are the possible factors? Plus or minus 1, plus or minus 3, plus or minus 9. Okay, I'm going to try A equals 3. So these are, remember, possible A values. I'm going to try A equals 3. So P of 3 equals 3 cubed minus 5 times 3 squared plus 3 times 3 plus 9. 9 and 9 is 18, and 27 is 45. Minus 45, well, look at that, 0, so that is a factor. So x minus 3 is a factor. So let's use A equals 3. So A equals 3. And let's synthetically divide this one right here. So that's 1, negative 5, 3, and 9. And look at that, r equals 0. So this is x minus 3 is a factor. What's left over, folks? X squared minus 2x minus 3. Okay, so the last part here is I need to factor that. And then we're almost there. So that factors. So I need to factor as x minus 3, x plus 1. Okay, and then let's put it all together. So lots of work going on here. Let's put it all together. I have that as a factor, that is a factor, and then that one and that one. Okay. So what do I got? Let me line it up first. Factors. X plus 2, x minus 3, x minus 3 again, x plus 1. Okay, and then it says fully factored form. So p of x, we started out with this. So let me write it out. And we ended up with this, a fully factored form, x plus 2 times x minus 3 times x minus 3 times x plus 1. Verify graphically. So when we verify this graphically, here's my window. What does this look like? This is what my function looks like. It kind of just bounces off. It's like tangent to the 3. We'll discuss what that means in another lesson, but that one, another reference point 18, so there's one factor. There's another factor. Okay, and then this one, remember when we had those perfect square trinomials and we graphed them as quadratics, and you get this parabola where the vertex of the parabola is just touching the x-axis. And how many roots were there? Or how many zeros? There's actually 2, but remember the 2 identical real roots, right? So just as an aside, if you graph, this is a PST, perfect square trinomial, you'll get identical, 2 real identical roots, right? And when you graph this, remember you get this deal, right? That's at 1, and it looks something like this, right? Same thing happens for a higher degree polynomial when you have repeated roots. These are 2 real but identical roots. We still have to write them 2 times, right? You can't just write it 1 time. That changes the degree of the polynomial. There are 2 real identical roots. So when you have the 2 real identical roots, it does this weird thing. So let's just label this as x minus 3. I don't know, it kind of bounces off the x-axis, but doesn't cross, but doesn't go across. Okay, keep that in mind for a later lesson when we talk about when roots are repeated like this, identical roots, sometimes 2, 3, 4. You can have as many roots repeating as possible. You get these really wild looking graphs. Okay, so just keep that in mind. Okay, so we got one more example, folks. Okay, example 6. Given that x squared plus 2x minus 3 is a quadratic factor of f of x equals x to the 4th plus 2x cubed minus 7x squared plus ax plus b, algebraically determine a and b. Okay, if this quadratic is a factor of this quartic, so this is quadratic, this is a quartic function, degree 4. Then the factors of this quadratic, which is, if I factor this, that's x plus 3, x minus 1. That's an a value of negative 3, and that's an a value of 1. These factors are also factors of the quartic. Okay, so we can use that fact for a equals negative 3. Let's do some synthetic division. And notice I don't have numerical coefficients, but I have them in variable form, so I'm going to write them down accordingly in my synthetic division. Okay, negative 3 times negative 4 is positive 12. A plus 12 is a plus 12. Negative 3 times a plus 12 is negative 3a minus 36. B plus negative 3a minus 36. So follow all the same steps that you would. I get b minus 3a minus 36. Okay, and since this is a factor, we know that the remainder must equal 0. So I'm going to say all of this remainder, b minus 3a minus 36, equals 0. Let's keep that off to the side. Let's take care of the other factors. So we did a minus 3 equals negative 3. Let's do a equals 1. Okay, so same thing, synthetic division. A plus negative 4 is a minus 4. And then 1 times a minus 4 is a minus 4. B plus a minus 4 is b plus a minus 4. And because this is a remainder, this is a factor, the remainder must equal 0, so I'm going to say equal to 0. Okay, 2 unknowns in 2 equations. How do I solve? I use a system of equations. Okay. I have b minus 3a minus 36 equals 0. B plus a minus 4 equals 0. Let me just clean that up. B minus 3a equals 36. B plus a equals 4. This is convenient. I'm just going to subtract. B minus b is 0. Negative 3a minus a is negative 4a. 36 minus 4 is 32. A equals negative 8. Let's find the value of b. So if I have b plus a minus 4 equals 0, I have b plus negative 8 minus 4 equals 0. B minus 12 equals 0. B equals 12. A equals negative 8, B equals 12. So I'll let you check that. You can do this on your own or look in the notes. You can check it and see if it works. But these two are good. A equals negative 8, B equals 12. Okay, one last note. For this course, we're not going to deal with non-integral zeros, but you should understand the concept. Some polynomials do not have any integer zeros, such as p of x equals 2x minus 1, 3x plus 4, 2x plus 5. But we should understand that the zeros of the polynomial are, so 2x minus 1 equals 0, x equals 1/2. So this one, x equals negative 4/3. This one, x equals negative 5/2.